Let's start this video with a definition. We say that two numbers, a and b, two integers, are coprimes if and only if the greatest common divisor among them is 1. When we have two coprime numbers, we're gonna write it as this: a, the symbol b. Before starting with some examples, let's have a look at this observation. A and b will be coprimes if and only if we can write 1 as a linear combination between a and b. The reason for this is, well, if a and b are coprimes, then the GCD between a and b is 1. And then we can use Euclid's algorithm, and we know that there will exist S and T such that the GCD, which is 1, can be written as S times A plus T times B. And if we have that 1 can be written as a linear combination between A and B, then with what we saw last video, we know that the greatest common divisor between A and B will divide 1. And if this happens, then we know that the greatest common divisor between A and B is 1. Let's now see a few examples. 103 is coprime with 98, and this is because the only common divisor they have is 1. 12,202 is not coprime with 43,554. These two numbers have a common factor of 2, and so they're not coprime. If a number a is coprime with 0, then a is plus or minus 1. It also happens that if a is plus or minus 1, then a is coprime with 0. We also have that for every v an integer, plus and minus 1 is coprime with b. Let's now see this proposition. We have 4 integers, and c and d are not 0. If these integers satisfy that c divides a, d divides a, and c and d are coprime, then c times d will divide a. Also, if they satisfy that d divides a times b, and d is coprime with a, then d divides b. Before trying to prove this theorem, let's see how important these two hypotheses are. For example, if we take a equal to 12, c equal to 6, and d equal to 4, then 6 divides 12. This is c divides a. And 4 divides 12. This is d divides a. But 6 times 4 does not divide 12. 6 times 4 is 24, and 24 does not divide 12. So that makes this hypothesis very important. For our second point, if we take a equal to 2, b equal to 3, and d equal to 6, we know that 6 divides 2 times 3, so d divides a times b. But 6 does not divide 2, and 6 does not divide 3. This tells us that this hypothesis is very important. So what we're gonna do is not prove this proposition exactly, is prove another one very similar. We will be proving the following. If we have that c is coprime with d, then c divides a and d divides a if and only if the product c times d divides a. And if we have that d divides a, then d will divide the product a times b if and only if d divides b. let's start with the proof. This is our hypothesis. C is coprime with D. So the GCD between C and D is 1. Then with Euclid's algorithm, we know that there exists S and T such that 1 can be written as S times C plus T times D. Multiplying both sides by A, we get that A, this is A times 1, equals S times C times A plus T times D times A. So now if we had that D divided A, this hypothesis, then C times D divides C times A. And we also had that C divides A. Then what we get is that C times D will divide D times A. So we have that CD divides CA and CD divides DA. Then CD will divide any linear combination between CA and DA. So what we can conclude is that CD will divide S times CA plus T times DA, and this equals A. We also had to prove this other proposition. Our hypothesis tells us that D and A are coprime. Then 1 can be written as S times D plus T times A. Now multiplying on both sides times B, we get that B equals SB times D plus TV times A. But D divided A times B, and D divides itself. So D will divide any linear combination between AB and D. So D will divide SB times D plus T times AB. And this is exactly the definition we had for B. Let's now try and solve this example. We have A and B coprimes. Then we have to prove that the greatest common divisor between 2A plus B and 3A minus 2B is either 1 or 7. Before starting to prove this, we actually have to believe it. So to do this, I'm going to take a few examples. If A equals 1 and B equals 0, then 2A plus B is 2 and 3A minus 2B is 3. Then the greatest common divisor between 2 and 3 is 1. If A equals 1 and B equals 1, then 2A plus B is 3 and 3A minus 2B is 1, and the GCD between 3 and 1 is 1. If we take A equals 3 and B equals 1, then 2A plus B is 7 and 3A minus 2B is also 7, and the GCD between 7 and 7 is itself. So it makes sense to prove this. We can actually believe this proposition that if we had two coprime numbers, then the GCD between these two numbers is either 1 or 7. Let's prove it. First we're gonna take D, a common divisor between these two numbers. D divides 2A plus B, and it divides 3A minus 2B, because we selected it as a common divisor. Then D will divide these two numbers multiplied by any constant. So t will divide 3 times 2a plus b, and it also will divide 2 times 3a minus 2b. Then, doing the calculations, we get that t will divide 6a plus 3b, and d will divide 6a minus 4b. We saw in a previous video that if a number divided two numbers, then it would divide the sum of those numbers. Then d will divide 6a plus 3b minus 6a plus 4b. 6a and 6a give us 0, and then here we get that d will divide 7b. But now we can do the same and say that d will divide 2 times 2a plus b, and it will divide 3a minus 2b. This is exactly what we had here, and this other number is this one multiplied by 2. Doing the calculations, we get that d will divide 4a plus 2b, and it will divide 3a minus 2b. So again, we can add these two numbers up and get that d will divide 4a plus 2b plus 3a minus 2b, which equals to 7a. So what we got is that d has to divide 7 times b and 7 times a. So the maximum of the divisors between these two numbers will be either 1 or 7, which is exactly what we wanted to prove. Let's look at the last proposition in this video. Whenever we have two integers that are not both 0, then we have that a divided by the GCD between a and b is coprime with b divided by the GCD between a and b. Before proving this proposition, let's see what it's actually telling us. We know that the GCD between a and b divides a, and using the definition of divisibility, then there exists an integer k, 1, such that we can write a as k times the GCD between a and b. So now if we divide on both sides by the GCD between a and b, then a divided by the GCD equals k. And this is the number we have here in the proposition. And this very same thing applies to b. So the GCD between a and b divides b. So there exists another integer k2 such that b equals k2 times the GCD. Now dividing on both sides, we get that b divided by the GCD between a and b is equal to k2, which is this number we have here. So what this proposition is telling us is that these two numbers are coprimes. Let's prove it. Thanks to Euclid's algorithm, we know that the GCD between a and b is equal to some integer s times a plus another integer t times b. Then dividing by the GCD, we get that the GCD between a and b divided by itself, this equals to 1, is equal to s times a divided by the GCD plus t times b divided by the GCD. So we were able to write 1 as a linear combination between these two numbers, then these two numbers are coprimes, which is exactly what we wanted to prove. To finish this video, let's solve an example. We have an integer a such that the GCD between a and 8 is 4, and we ask ourselves what values can this number take, the GCD between a squared plus a plus 32 and 16. So the only thing we know about a is that the GCD between a and 8 is 4. So using the definition of GCD, we get that 4 divides a. Now using the definition of divisibility, there exists an integer k such that a can be written as 4 times k. So 4 is the GCD between a and 8. But now a is 4k, so 4 is also the GCD between 4k and 8, but instead of writing 8, I'm going to write 2 times 4. Now we can factor out the 4 and we get that this is the GCD between 4 and k and 2. So now when we divide by 4, we get that 4 divided by 4 equals the GCD between k and 2. So the GCD between k and 2 equals 1. Then k and 2 are coprimes, which tells us that k is odd. Now let's work on the thing we actually want to find. A squared plus a plus 32 and 16. Again, we have multiple times a, and a was 4k. So a squared will be 4k squared, which equals 16k squared. Then we can write this as 16k squared plus 4k plus 32 and 16. But now we can factor out 4 and we get this is 4 times 4k squared plus k plus 8 and 4 times 4. We can factor out the 4 out of the GCD and we get that it equals 4 times the GCD between 4k squared plus k plus 8 and 4. All we know is that k is odd. So this number, 4k squared plus k plus 8, the GCD between this 1 and 4, has to divide 4. Then this number can only be a member of the set 1, 2 and 4. We know that 2 does not divide 4k squared plus k plus 8 because k was odd. So this GCD has to be 1, but the one we were trying to calculate was this one, which is 4 times this. So it will be 4 times this, which is 1 times 4. And we have our solution. Then the GCD between a squared plus a plus 32 and 8 is 4.